Hi, in this tutorial we will study edge detection. We will define an edge in an image as a significant, and look at how I'm highlighting, or I circle the word significant, local change in the image intensity. So look into these examples to see if we get the main idea of the definition. So in this first example, this is an image. We have a circle, so this is like a solid circle, so this is the background. So if we go into the image intensity values from, let's say, from right to left, we have a constant value in the intensity colors for the image, and then when we get into the edge of the image, and then we actually get into the image, there is a change. And that's what we're going to say, well, there was a significant change. So here it wasn't, let's say, that significant in the background because we are still in the same object. So we reach in the edge of the object. So in this case, the local change can be seen of what we said a step discontinuity. So look at that, this line, has some type of a constant value, and then suddenly there is a change, and then there is another value. So that's what we said, oh, there was a significant local change. And then that's what we said, this is probably where we have an edge. Okay, and the next example, in this circle, you see that we have the same idea. We got the background, so this is kind of constant. Then we got an edge, there is a change, and then we're going back to the background. So this type of change is the one that we're going to align discontinuity. Now, the previous examples that were explaining like what the idea or what was a significant change, but because of the smoothing or low frequency chart discontinuities in an image, the chart discontinuity in an image are very uncommon. So what we were looking into a step function is actually a ramp. So that means that maybe it's not a sudden change like that, and I think that makes sense. There may be different factors that can influence that in a RGB image, and the same with a line becomes kind of like a roof. And again, we can think on several reasons that can happen, and basically is that it is more in the low frequency and so on. Well, so once we understand the problem of edge detection, as seen detecting the local changes in an image, then we need to see how is that we can develop an algorithm to be able to actually find edges in images. So we will borrow some concepts from calculus and maybe even from something from algebra about local changes. Like first we're going to see an image. In this case, I have here this array as a two-dimensional function, or a function of two variables. For x and y representing the position of a given pixel, and f will give the value of the intensity value in that location. Right, so here we know we have seen that an image is a matrix of an array of numbers. So what this also can be seen as a function that in this case will be two variables. And what I have here that says a possible definition, it will be ideal if for every image we can find a representation of a function. Like, for example, let's suppose that this is the actual representation of a image of, I don't know, this represents maybe a face, or maybe represents something. It will be great if we just do the substitution of whatever is the location and give us the intensity value there. Then we could do wonders if we can have that. Because we can zoom in, zoom out, do a lot of things with the images, right? But this is not the case, that we don't have the representation, we just have a sample of that possible function. So for that, then we're going to have to do some type of numerical analysis. We have to do some type of approximations, because this will now be known. Now, how is that we're relating that with the first derivative? Because the first derivative of a function represents the rate of change, and that's what we want. Remember that the edge we defining as a significant change. So we need to find something that will give us the sense of change, and for that we're going to go into the derivative. Now I said that maybe we're going to get something from algebra. I'm sure that you were working in algebra with a slope, which is also the rate of change. Like for example, there is a line, there are 2 points, x1, y1 will be the first one, and the other one over here, x2, comma, y2. And then you may remember that you get the change in x and the change in y, and then you get this ratio that you call the slope, and this also the rate of change. But how is that related with the derivative? Well, when you do the definition of the derivative, you say, well, that rate of change in the x, we're making that really small. So here, the y1 and the y2 in my function represents the f of x and the f of x plus h. So this in this function, I'm moving from the x to x plus h, so the distance is h. But when I apply the limit, when h is really small, that's what we call the first derivative, and that's the one that is going to give us a rate of change. Now, we just have a problem. So here we kind of relating now the idea of how we're going to work with this. So the problem that we have now is that, okay, the slope is a good idea. Is just that this change in x may be too big. We're making that a small change, and then we get the first derivative. Now the other problem, this is a function of one variable, which is the one that you maybe saw in your first calculus class. And then you know that this concept can be extended into a function of 2 variables or multiple variables, and that's what we call the partial derivatives. So here is the idea. I'm just giving the idea of the rate of change here, and then in the slope, and then how this is interpreted in the first derivative for a function. Now if we got a 2-dimensional function or a function of 2 variables, that function now, instead of represents just a curve, represents a surface in the 3D space. And then we got a region here, and then there are some changes in the region. This region can be what I have represented here. So there is an x and a y, and then there is a change in the direction of the y-axis, and then maybe there is another change in the direction of the x-axis, and then the changes again are h. So then I have 2 derivatives. So here there was a change only on the x, the direction of the x-axis, and that's what we got that. Now when we got 2 variables, x and y, I got 2 possible definitions, right? So here is a change in x, and y is constant, and here x is constant, and there is a change in y, and that's what we're going to call the partial derivative, and this is the notation for the partial derivative. Or sometimes we call it f sub x, which means this is the function and this is the partial derivative on that direction. Again, we are just going in to find intensity values and how we make an approximation. But once we understand this, then we say, well, again, we don't know the function, and we are not able to actually compute derivatives in using software, I mean the actual derivatives. So what we do is, well, we're going to have approximations, and then different ways of solving the problem of edge detection will be different ways of how we going to interpret or how that we will work on approximating derivatives. So here I have an example of a function of 2 variables, which is 3x squared y plus 4 times y squared minus 5, and then I'm just asking that if we can compute the partial derivatives, just to have a sense of what is happening in case that you don't have really fresh on your calculus classes. So it says here using the definitions. So the definition says that, this is my input, the f of x, comma y, and then I just need to get the f of x plus h, comma y, and the f of x y plus h. So here is just the explanation. If for example, in the case of f of x plus h, comma y, you do the substitution of the x's for x plus h, then you just do the simplification. So what I'm doing here is the substitution in the definition that I have here. I said that I'm going to subtract these two functions and then divide it by h. Once I simplify, I substitute the h by 0, and that's my limit. So this is what I'm doing over here. So I'm doing that, and I'm simplifying, and then I get this expression, and once I apply the h equals 0, my answer is 6x comma y. Then from there, you have to maybe derive some type of formulas that says, okay, if this is the input, and then if I'm doing the partial derivative with x, I said, okay, only x is the one that changes, anything else is constant. Then if you apply formulas, it's 2 times 3, 6x, and then the other is just constant. Here there is no x, and there is no x, and the derivative of constants is 0. Okay, so here, applying the definition is the same. What I'm doing for the definition is going into this expression that is over here. I need to find the x and the f of x comma y plus h, and then subtracting f of x comma y and divided by h. We simplify, and then we substitute the h by 0. And this is what I have over here. I'm finding the f of x comma y plus h. This is the expression. So I'm putting the expression over here. You do the substitution, simplification, and then we subtract the f of x comma y. Once we simplify, divided by h, this is the expression that I have here. Then we substitute the h for 0, and this is what we get. Now, this was using the definition. If we were using some formulas for finding the derivatives that you studied in calculus, we can have something like this. If I'm doing the partial derivative with respect with y, only y is the one that is changing, and anything that is not a y is a constant. So here the only thing that changes is y, so the answer here, the derivative of y is 1, so it's 3x squared. This is the answer. And then here this will be 2 times 4, 8 y, and this is what we have over here, and the derivative of a constant is 0. So it's just an illustration of the way that we compute it. Okay, so once we have that review, the next part is how is that we're going to do the approximation. And for that, this is the last part of the tutorial in which we will think, or say, how is that we can approximate that we are not actually going to be able to ask the computer to perform a derivative on a function that we don't know. So what we said is, when we got an image, we place the image in x and y coordinate, and then we said, well, this is what we have. And remember that the idea of the h is the smallest possible change that we have in the x direction and the y direction. Now, because we're talking about pixels and location of pixels, the smallest possible distance between another pixel and another pixel will be 1. So my h will be equals to 1. Then when I'm doing the approximation of the partial derivative on the direction of x, it will be the simplification of the function will be this, where the h will be equals to 1. So we're doing the approximation. So we have this formula. So in this case, my smallest possible h is 1. So I'm dividing by 1, and then this is what I have. So which means it's just subtracting the intensity values of the pixel, like for example you see here in this graph, which be the pixel over here and minus the intensity value of the pixel on the top. And then if we do the same, and then this is for the y, and then for the x-axis in the x direction will be the subtraction of these 2 pixels, in the y direction the subtraction of these 2 pixels. So I'm glad that we were working with the filters. In filters, we were using a mask or a kernel to do the convolution. This will be equivalent of doing the convolution on that point. So you do the convolution using this mask, the -1 and -1 over this point. This is how we will do the approximation of the derivative. So in the next tutorial, we're going to go into some of examples of applying this mask, but this is the summary of the important part of the edge detection that we're going to do, which is that we got the -1 and the 1 and the -1 that will be the mask or the kernel that we're going to use for the convolution, and that will be the way that we will do the approximation. So now we just need to interpret the results that we're going to get by using this.